Okay, hello again. So I'll just start with a review of what I talked about yesterday. So what we had is, we were considering a Hermitian one matrix model. So we chose an ensemble of L cross L Hermitian matrices. And I hope today I'm not going to mess up any notations. So my matrix will always be denoted by H and my rank will always be denoted by S. And then we defined our partition function. This is a partition function. This V here is the potential, which I'm going to take it to be an infinite power series. And then we wrote it down in terms of the eigenvalues. So this measure DH in terms of eigenvalues looks like this, and the potential just becomes a function of the eigenvalues. Then we saw how do we calculate correlators in this matrix model. So we basically saw the genus expansion of the correlators. We did not actually calculate them. So what we did is we first, as an example, we first talked about the Gaussian matrix model, and then we saw that just following the same prescription, we can write the correlators of any generic matrix model. So if we try to draw Feynman diagrams, we have a double line notation for that because the fields here are matrices, so each of them carry two indices. So we draw our propagator like this with two lines, and we put the indices I and j with those two lines. So this is the propagator that we have. It goes like 1 over L. And then since our potential is a power series potential, so we have all the powers of H, say H cube, H to the power 4, and so on. So we have an infinite number of vertices coming from the potential. And then we also saw that if we want to calculate some correlators, say if we want to calculate the correlation function or the expectation value of some function which is trace H to the power mu I, then we can interpret this as this H to the power, if mu I is say 4 or if it is 3, then we can interpret it like these 4-point or 3-point vertices. And to get all the Feynman diagrams, what we have to do is we have to do all possible contractions of these vertices. So in general, if we have say n insertions of these operators, then what we do is we'll draw the vertices corresponding to these insertions, and then we'll have an infinite number of vertices coming from the potential, and we draw all possible contractions. So since the vertices coming from the potential and the vertices that we are drawing for the insertions are different vertices, so we have to make sure that those are not mixed up. So we have to label them differently to make sure that you can identify which one of the vertices is which one. So that is why I've drawn the vertices coming from potential with blue and the potential that are the vertices that are coming from the insertion with yellow. Okay, so then I talked about this theorem, which tells us how can we think about these endpoint correlators. So if we want to calculate a correlator of this sort, then what we have to do is we have to sum over all these graphs, which we get by these contractions of the double lines. And the factor of L for each of these graphs goes like chi, which is nothing but the Euler characteristic of that graph, given by 2 minus 2g, where g is the genus of that graph. And if you talk about it in terms of the vertices, edges, and faces, then it is just v minus e plus k. Okay. Then we talked about the dual surfaces of these graphs. So if we have an endpoint vertex, then the dual of that vertex is given by an n-gon. So say if we have a 3-point vertex, then we have a triangle. If we have a 4-point vertex, then we have a quadrilateral. And if we have a 5-point vertex, we have a pentagon, and so on. So since yesterday there were some confusions with this marking, so I've tried to draw it a little better here again. so that we can see what is the difference between the diagrams that we have when we do not have any insertions, that is when we are just calculating the partition function, and the diagrams that we get when we have some finite number of insertions. So yeah, before that, so like I said, we can draw the dual n-gons of any endpoint vertex. So if we have some arbitrary ribbon graphs like this, then we can just keep on drawing the duals of each of these vertices. And ultimately what we are going to get is a surface which is discretized with some polygons. So we can also say that the correlators are just given by sum over some surfaces of genus G which are discretized with some polygons. So let's say I have some insertion of h cube and h to the power 4, and I have this some arbitrary diagram. So what I mean by marking these vertices is, so this orange lines here correspond to the vertices that I get from the potential, and the vertices that I get from the insertions, those I have marked with green. And then I have drawn the dual polygons of these vertices. And this red thing is basically these red lines are the markings of those polygons. So when we have some finite number of insertions, the correlator is given by sum over an infinite number of surfaces of genus G. But now what we have is we have the discretization of a surface, but some of the polygons on that surface are marked. And then what we said is we can interpret this marked surfaces as some holes in the surface so that we have a nice genus expansion. And we can say that the correlator is just given by a sum over surfaces of genus G and n holes. So then the Euler characteristics is given by 2 minus 2G minus n. Then we can write a similar sort of
one question.
Somebody, your voice is not clear.
Noise from your end.
Rita, I kind of muted you, but there's a lot of noise.
Is it okay now, or is it still not? There's still noise.
It's good now. It's good now.
Okay. Yeah. So what I was asking is that in the potential you showed that it was sum over h to the k, means the different point vertices. So why is this trace required? Means it seems.
So what I said is that we have a symmetry in the partition function, which is just the diagonalization of the matrices. This partition function is symmetric under H goes to U lambda U dagger, where lambda is the diagonal matrix with all the eigenvalues, U is the diagonalizing matrix. So our partition function is symmetric under this. So if I just put V of H, then it will not be invariant under this. That's why I need a trace.
So I have to take the trace. Thank you.
Okay, so is this discretization clear now? Okay, so also, so somebody was asking me for an example of the dual surface, and I would like to mention that yesterday I was not being careful while drawing the dual graph of the trace m to the power 4 that we had. So I'll just clarify it now. So what I yesterday draw for, so I had this diagram, and I just said that you can draw a dual like this. So this is not actually the dual of this graph, but the dual of this 4-point vertex. So I'll now explain how do we draw the dual of a graph. So say, for example, we have this graph. So in a dual graph, what we have is in each loop we have a vertex, and for each propagator we have an edge. So I mean, this is one of the examples. So if you say, and like to just see how, I mean, just to make sure if you're drawing your dual graph correct or not, you can count the number of the edges, vertices, and faces. So if you start with the graph which has E number of edges, V number of vertices, and F number of faces, then your dual graph will have the same number of edges, but the number of faces and vertices is flipped. So if you initially had F number of faces, in the dual graph, you'll have F number of vertices. And if you had V number of vertices earlier, now you'll have V number of faces. So this is one of the example, and I will leave it as an exercise to figure out that this is a correct dual graph, and you can do all the countings to make sure of that. And then you can also
Sorry,
try
Neetu, can I ask a question?
Yeah.
So in the previous slide, you talked about duals of these vertices, right? And you're saying that dual of a graph is different from the dual of a vertex?
Okay, so the point is, I mean, to draw the dual of a graph, what you're essentially doing is you are drawing the dual of these vertices. But the diagram that I have here, it has some external legs. It is not a connected diagram. So when you have, if you just the propagators that I have, for example, these and these, if you close these loops, then there'll be some non-triviality. You have to be careful while drawing the dual graph. And that is why I said, like yesterday when I do this, I was not careful.
Oh, okay. So let me just.
So here, if you see, I have cut I have two propagators, but I have drawn 4 lines. So I've cut each of the propagator twice. I should not do that by drawing dual of a graph.
Okay. So can you just go back to the slide one second? So what you're saying is that before I join these external propagators, I can't actually draw the dual graph, is it?
Yes, I mean, it's a high chance that you might get it wrong.
Okay.
Okay, so this gives us the genus expansion of our correlators, and any function of these matrices H, we can write like this. Okay.
Sorry,
So,
I have another question. So with these marked polygons that you had, you were saying we can think of those as sort of poles in the.
Yes, while counting the Euler characters, these are not really the holes, but just to make this expansion look nice, we can say that the power of L is given by the Euler characteristic, but which is the Euler characteristic of a surface with genus G and N holes.
So sorry, so the number of these marked surfaces will directly give you the Euler characteristic? Is that what you're saying? Sorry, I didn't understand
You need both genus and number of holes to calculate the Euler characteristic.
Oh, achha, sorry. This small n is the number of marked surfaces.
Yes.
Okay. Yeah, sure.
Okay. So, yeah. So our next goal is to calculate these functions, and we started with the calculation. So, so we talked a little about the saddle point analysis, and for that we started with a partition function written in terms of eigenvalues. And what we did is we just left this measure d lambda I here and took everything in the exponential to write it as an effective action. And we saw that there is a repulsion between these eigenvalues. There's this potential which we have provided, and then there is this repulsion between the eigenvalues which comes from the measure. So the eigenvalues are distributed around in some interval around the minimum of the potential. And in L goes to infinity limit, the dominant contribution to this partition function comes from the saddle point of this effective action. So to calculate the leading order result, what we have to do is we have to solve this saddle point equation. And explicitly, this is the equation. Then since we are dealing with a larger limit, we have a large number of eigenvalues. So we introduce some continuous variables. X, which is I over L, and we wrote our saddle point equation in the integral form. Here this P denotes the principal value integral, and rho naught is the larger limit of the eigenvalue density. And then we went back to this function resolvent, which we defined earlier. And so this is essentially, so since we are doing a saddle point analysis, we are just focusing right now on the leading order. So this is the leading order piece, R0, 1. So if we have n point correlator of the resolvent, this is how the genus expansion looks, and the leading order piece here is R0, 1. So this is what we are calculating through the saddle point equation. And from its expression in terms of the eigenvalues, we saw that it has pole exactly at the eigenvalues of these matrices. So this sort of this tells you where are your eigenvalues located, and we can also write it in the integral form. So when we have a matrix H and we have a set of eigenvalues, some lambda 1 to lambda L, so those eigenvalues have some fixed values. But when we do an ensemble average, what we are doing is we'll allow those eigenvalues to take all possible values. So in a sense, we are taking all possible points in a given interval. So if we take the ensemble average, this discrete function becomes a continuous one, and these poles are smeared into a branch cut. So this is the integral expression for the resolvent, and it has a branch cut along the support of the eigenvalue density. And from this definition, two things which are clear is that the discontinuity of this gives us the eigenvalue density, and V prime E, which we can figure out by looking at the saddle point equation, is given by this expression. Okay, so is there any question till this point?
I have a question. Can you go to the previous page?
Yes.
So in the last equation is RGN. So you are taking R01, 02. So like why you are varying like N is fixed, no? G is only like summed up. Why you are taking different values of N?
Yeah, but if I want to calculate the resolvent, I'll just take RE1.
Okay, for R01 you will take only the RE1, like the 0 to U.
Rito, I have a question.
Yeah, so what I was asking is that normally when we, like in case of partial function or whatever, when we do a saddle point analysis, typically it's like the classical solution, right? And then we find the quantum about that solution. So here, is it like some analog of the classical? Because here seems the potential as all possible vertices and you're solving this.
Yes, so this elsewhere, what we usually have in a path integral is dx e to the power some 1 over h cross s effective.
Right,
So we can identify this elsewhere with 1 over h cross, and our classical limit corresponds to h cross goes to 0, which is nothing but L goes to infinity here.
Okay, but like in a given problem, your L is fixed, right? That is fixed by the number of loops.
No, I mean, you can do as, so if you're taking say QCD and you say that your gauge group is SU3, then your L is fixed, and then the calculations will be very complicated. But when you're talking about when you're talking about some random matrix model, it's up to you what you want to choose. You are saying this L is the rank, L is some number which is the rank of your matrices. So you are not really fixing L here.
Okay, so your L expansion is analog to the genus expansion, kind of. Is that the?
Yes.
Okay. Thank you.
Okay. So let's now calculate the expression for this function R0, 1, and it will just follow from its properties. So first what we do is we define this function sigma of x, which is x minus a minus x of x minus a plus, where A minus to A plus is the support of my eigenvalue density. So here I'll be considering the case where my eigenvalues are distributed only in one single interval, which is known as the one-cut solution. In general, it can have many disjoint intervals, but I'll only be considering this case. So once we define this function, so for large x, square root of sigma x goes like x. And this square root of sigma x is also discontinuous along the real axis. It also has a branch cut between A minus to A plus. So if you vary it across the real line where the support of where rho is supported, then it changes sign. So what we are going to do is, so let's just use the residue theorem and write an expression for R0, 1. So what I'll do is I'll write a contour integral about the point E. So this just follows from the residue theorem. Let me just draw a figure here. So let's say this is some point E, and here is my support, A minus, A plus. We know that this resolvent has a branch cut between A minus to A plus. So what I'm doing is I am taking a contour about this point E. Now, if you look at the expression of R0, 1 lambda, this is B lambda prime, rho lambda prime, lambda minus lambda prime. So for as lambda goes to infinity, it goes like 1 over lambda. So there's no pole of this function at infinity. So what we can do is we can deform this contour around E to a contour around this branch cut. Okay. So that's what I'm going to do.
Here the integration
I
range of
might
lambda
have
prime
drawn the-
is sorry to interrupt. Here the integration range of lambda prime is 0 to infinity.
Oh, I couldn't hear you properly.
The integration range of the R01 lambda expression that you wrote.
Mhm.
Here, if the limits are infinity, then can we say that there's no pole at infinity?
There is no pole.
It's you say that there's no pole at lambda equal to infinity.
Yes.
So will you please, can one say
No,
that?
I didn't get your point. What are you trying to say?
I'm saying that if the integration limits are like say from 0 to infinity,
Mhm.
then the integration is over lambda prime. So at lambda prime infinity, there seems to be a pole. Right? Maybe
What I'm saying is you can do, so this is an integration over lambda prime, right? But you can do an expansion in lambda.
Yeah, but means if the integration range is infinity, then can we like say this, that it goes as 1 over lambda as lambda tends to infinity? That is all. Means if lambda prime was fine, if the limits are finite, say a to b, when a, where a or b are finite, then I I agree that this will go as 1 over lambda.
So rho lambda is supported between a minus and a plus. So even if you put your limits from minus infinity to infinity, the integral will be 0. I mean, apart from
Rho lambda
the support
prime.
of rho.
Yes. Okay, thank you. Yeah.
Is that fine?
Yeah. Thank you.
Okay, so now this contour is around the branch cut. Now, once we write this integral about this branch cut, then we have to be careful where are we choosing our r0, 1, because it is different if we approach the real axis from here, and it is different if we approach the real axis from here. So, what we notice is that the function, this function that I defined, square root of sigma x. So, say if you take this integral above the axis, then you have this function, say root sigma lambda. And when you define it below the axis, then since this also has a discontinuity, this changes sign. So you'll get a minus square root sigma lambda. And because of the orientation of the contour, your lambda will also change sign. So overall, the integral will not have any sign. So we can use this property, and we can write this r0, 1 as we can write its average. We can replace it with its average value, which is nothing but v prime lambda. V prime lambda over 2. So ultimately, we can take an expression like this. So now this looks like an expression which is written in terms of the things that we that are input to our model. So now we know the potential V, so we can evaluate this expression. But there are still some unknowns here, because this function square root of sigma lambda, which is square root of lambda minus lambda minus a plus, involves the support, the endpoints of the support a minus and a plus. So these, we do not know what are these points. So we need to evaluate these points also to ultimately calculate r0, 1. And to find out a minus and a plus, what we can do is we can just use the asymptotic behavior of this resolvent, which goes like 1 over e. And once you evaluate the expansion from here to this, you will get two equations for two unknowns, which are like this.
Akhil has a question, so can you please?
Yeah, sure.
Akhil,
Hi, so
please.
A plus and A minus were the boundary, I mean, the region between which you are looking for lambdas, right? Between which all the lambdas are spread out.
Yes.
And so any sufficiently large A minus A plus, you could just substitute into this, and would it work? Or did I get it wrong?
Sorry, can you repeat?
I thought A minus and A plus were some points between which all the lambdas lie, right?
No, A minus and A plus are the endpoints of the support. So all the eigenvalues lie between these 2 points.
Right. So I mean, so I could like feed in as A minus and A plus any large enough number, right? Shouldn't it just go through?
No, but given your given a potential, what you're trying to find out is how are your eigenvalues distributed, or what I mean, you're trying to find out what are your eigenvalues. And since we are dealing with the large element, I'm saying that I'll not talk about the individual eigenvalues, I'll talk about their distribution. So this is essentially the information you're trying to extract here. Like what are your eigenvalues? So if you say that these A minus and A plus could be like, you can take them to infinity. When you start with your model, that is a true statement. That is always true. You have some real eigenvalues, they'll take values between minus infinity to infinity. But once you have given a potential, then this statement will be always true, but you are trying to extract some more information.
I mean, are we just not trying to calculate the resolvents the R0 ones and so on.
Yes, but what is R0, 1? That also depends on your model. That also depends on the potential that you have.
No, I'm trying to ask this. We know B and we know sigma up to A plus A minus. And A plus A minus by definition is some segment in which all the lambdas lie. So any large enough segment, I thought if I feed into this, I mean, I see it will change the answer, but maybe I'm confused about what is A plus and A minus.
Yes, you can, I mean, if you feed random values, then it will give you the answer for some matrix model. But if you want to calculate what is your support for a given potential, that you have to take into account your potential.
Then I think I missed the like how you defined A minus and A plus. Could you repeat that? Like I didn't probably understand what is A minus.
Sorry, just a related question. Could you just tell us how you go from having a potential to getting these bounds on A plus and A minus, or getting the values for A plus and A minus?
Yeah. So the idea is we started with this partition function, okay, and we have given some potential P of lambda j. Okay. Now this factor that comes from the measure tells us that no two eigenvalues can sit on each other. There is a repulsion between these two. So what you effectively have, you have L number of eigenvalues, and the potential that each eigenvalue feels is given by a combination of this potential and the repulsive potential that is coming from here. So in a normal situation where you have some potential, then what you'll say is that the saddle point is the minimum of that potential, right? So you'll say that the equilibrium configuration will be when all the eigenvalues sit at the minimum of the potential. But because of this repulsive part, all the eigenvalues do not sit at the minimum of the potential, but they get spreaded along the minimum in some finite interval. And those are, so in general, what can happen is your potential can have n number of minimas. Then your eigenvalues will be distributed in n intervals around those minimas. What I'm saying is I'm just considering the simple case where I have only one minima and my eigenvalues are distributed in some interval from A minus to A plus. And now what I'm trying to do is I'm trying to find out what are the exact values of this A minus and A plus given a potential V.
So A minus is the value of your smallest eigenvalue.
Yes.
Okay. And A plus is the corresponding largest eigenvalue.
Yes. Is it clear now?
Okay. Okay.
There's
So
another raised hand.
then maybe could you also say like what happened when you introduce that sigma function? Like so that part is kind of unclear to me.
What happened when I introduced the sigma function?
Why did you introduce and what happened? Like, yeah, what is the manipulation?
I introduced it so that I can write down an expression for R0, 1. So this is something that I introduced for my convenience. Like you can say that it's a trick to write down an expression for R0, 1. And this is one way to write down this expression for, this expression for R0, 1. What I'm telling you is one way to write it, but you can also derive it in other ways. And I don't remember the name, but there is a theorem that exists in mathematics. I'll share it in Slack. And from there also you can, using that theorem, you can also derive this same expression. So this sigma function, I just defined it for my convenience.
Shovik has a question, so.
Yeah, is it correct that this A plus and A minus is the range over which the eigenvalue density is non-zero? Is that correct?
Yes.
Yeah. So I guess this I think addresses Akhil's question that if you take it large enough, I mean, say some large negative number to some large positive number, then there might be some region where the eigenvalue density is 0, but you want the range where the eigenvalue density is non-zero, and that's what A plus and A minus.
Yes, it's like she's being more specific, right? She's saying A minus is the minimal and A plus is
Yeah,
the
yeah,
maximum,
yeah.
right?
Yeah, which is the same thing.
Arthur has a question.
It's more of a comment. So as Souvik mentioned, I mean, it covers all the bits. But one more thing, I mean, Neetu could have just shown. So when he is putting S prime to 0, so basically you have an equation that you already know the action in terms of the potential, right? Then what you can do is you can write the equation of motion. That's the subtle point thing, right? You can write the equation of motion. So if you put S prime to 0, then what you can see is that you write the equation of motion in the large n limit or whatever, because she's doing the large n limit. So there you can directly see that whatever your potential is, okay, that potential is connected with the eigenvalue distribution. See, if you just go back to one slide where you have the action, one more. Good. So see here, if you just take a derivative of this S effective, you see 1 by lambda I minus lambda j terms goes down, right? And you get a V prime, potential prime on that, right? So what you are getting is basically you have to solve an integral equation, what you will have at the end of the day. When you do this large n limit, what will you have is you have to solve an integral equation. Whatever she is doing is basically a trick to achieve that. And now the first thing that you have to, since you have to solve an integral equation where the eigenvalues are distributed in the discrete limit, in the continuous, excellent. So in the continuous limit, your eigenvalues are basically distributed over some range of numbers that Souvik just mentioned. So eigenvalues are basically distributed over some part of the region, and that you can also see if you need to go back one slide up. Excellent. So you see there is this 1 by L part is sitting in front of the potential. So if you think about it as a effective action kind of thing, so you see there are two competing terms, one this log term and one this potential term. So potential term is a common term, I mean common potential where all the eigenvalues are technically moving. So there is a competition between these two. So though that competition actually tells you up to which part, or I mean on the real line, since this is Hermitian models, the eigenvalues are distributed, as Souvik was mentioned. So it's actually important to know where the eigenvalues are distributed up to which part. So those A minus A plus, whatever she wrote for R01, initially that's an ansatz. Go one step down, Neetu, please. Excellent. Now, no, where you have written this R01 equation, integral. Next slide, probably. Excellent. So R01, the upper 7th slide. Just yes. So here, whatever she is writing, it's the ansatz to solve that same differential, that integral equation, that R01. It's just an ansatz. So what you are trying to find out, put this ansatz back, then that will, this row red line equations, it will solve those red line equation. That's the ansatz, which will give you those red line equation, because that those are your constraints. So under that constraint, now you are trying to solve. So sigma is defined like that just to satisfy that ansatz. That red line equations. Okay, so it's just more of a comment. So go on.
Yeah, Arindam has a question. So
Yeah, sorry. So I just wanted to know if this row has to be differentiable everywhere. Like, is there a requirement like that?
This row have to be differentiable everywhere.
Like, yeah, is it a continuous differentiable function?
I think so.
No. So the reason I'm asking is that if it has to be differentiable everywhere, and the lowest and the highest eigenvalues that you have can have non-zero rows, then what Akhil was initially saying, that you can choose arbitrary A minus and A plus and say that row has a support there, doesn't make sense, right? Because then it can just at the boundaries of A minus and A plus, it can sharply drop, which will make it non-differentiable at those points.
One more assumption that you have to solve that is not here in these equations is that even if you solve this integral equation, which is the differential equation, the equation of motion, then you have to make sure that rho is normalizable, because that's your first, in some sense, it's an assumption that you are assuming that eigenvalue is differential, distributed over some range. So in that sense, you cannot take A minus. Other than that, the first assumption to solve this thing is that outside of the support, the rho is 0.
Right.
Yeah, you can just look at it on the definition. So this, if you just calculate rho lambda d lambda from, so since this is 0 and since the I mean, so I should not write lambda 0, but let me write this just p minus to p plus. This is equal to 1. You
Right.
can also check it from these definitions here. It will be clear.
Right. Thank you.
Okay, should I move on? Okay, so these are the two equations that we can solve to find out the values of a minus and a plus. So to get a full solution of the saddle point equation, what we have to do is we have to solve these two equations and then we have to evaluate this. Okay, now so this is how we find out R0, 1. Now we move on to the calculation of R0, 2. And for that, let me define some more things. So let me just write my resolvent again. We have this series expansion. So now we'll define an operator which is called the loop insertion operator. So given a series potential like this, so Vn, these Vn's are these coefficients. We can define this operator, the loop insertion operator, and let's operate it on the free energy. So f is nothing but log z. So we'll get 1 over z, del z over del v. And then we can use this expression. What we are going to get is so this part comes from the potential, and since we have a delta function, so one of the sum goes away, and ultimately we are left with this. And this here is nothing but the resolvent. So we have another expression for R of E in terms of the free energy. And we know the genus expansion of free energy as well as R of E. So we can also write this relation for each order. And if you just do a series expansion, this will be just L df0 over dv L and so on. And you write the genus expansion for R of E, which is LR0, 1, and so on. And you can compare these two. You will see that R0, 1 is nothing but df0 over dvp. Now you can keep on operating this ddv again and again on the free energy, and you can write a similar relation for all RGNs. So if you want to write your RGN, you have to act your operator n times. Okay, so now let's see what is R 0, 2. R 0, 2 is nothing but the dv of 2. 1. This is nothing but R 0, 1. So we can write R 0, 2 in terms of R 0, 1. Okay. Now we know the expression for R 0, 1, so we can substitute it here and evaluate the expression for R 0, 2. So let's do that. Let me just copy this expression. Okay, so what we have here in ddv, we have the derivative with respect to this parameters vn. So here in this expression, the potential depends on Vn and as well as the sigma depends on Vn through the endpoints A plus and A minus. So we have to take care of those things while doing the derivative.
Muktajyoti has a question, so can you please unmute yourself and go ahead.
Yeah, hello Neetu. Can we go from g equal to 0 to arbitrary g like you did for n?
Can you repeat, can you make it more clear?
Yeah, like this operator you are acting on f of g, it is inserting more n, right? So number of
Yes.
n is increasing. So can it be
Yes.
done for g also, the genus also?
I still don't get it actually. I mean, what you're saying is since I had R 0, 1, now I'm evaluating 0, 2 from R 0, 1. So are you trying to say if I have say 1, 1, can I also write it in like this with
Yeah, I mean,
some
can
lower
we
R
go?
G, n?
Can we get
That the
R1, 1 from R0, 1 by operating some operator?
Not just R 0, 1. You will need, I guess you will need both of these. So the point is that this is just suggestive of a recursive relation between all these RGNs, and there does exist a recursive relation between all of these. So if say you want to evaluate R1, 1, you'll probably need both R0, 1 and R0, 2. But once you know those two, you can evaluate R1, 1. So I'll come to that. Once we are done with the calculation of R0, 2, we will go to the loop equations. And those also like from the loop insertion operator that I defined, you can also derive those equations from this operator. So I'll tell you more about it later. But yes, there does exist a recursive relation between all these RG commands, and that is actually our ultimate goal.
Okay, thank you.
Okay. Let me just write a few lines of the calculation. I'll not do the full calculation. While doing this calculation, we have to be careful. Where do we put E1 and E2? Okay, so what we have to evaluate is this, and this. So instead of evaluating this, we can do some manipulations, and we can write the sum over n 2 to the power n plus 1 del n lambda. So this is just this. So this we can write like this. Okay, so this first term, in the first term, you can use this relation, and it will introduce this second order pole in your integral. Then we need to evaluate this derivative. So I'll just write the expression for this. Okay, so one more thing I forgot to mention, that in these calculation, I am simplifying it a little bit more by taking a plus minus as plus minus a. So I am taking a symmetric support. Okay, so once we have these two expressions, we can substitute them in the expression of R0, 2. Let me write it. Okay, so now still there are these terms which are which are not known. I mean, in a sense, if when you're evaluating your R0, 1, so you can find out your A plus and A minus from the asymptotic behavior, but instead of using those exact expressions, I just use the equations that we had to evaluate them, and then we can just use those equations to write this integral in a better form. So what I'm going to do is, since I just need this, I need this derivatives of A. So what I'm going to do is, I'm going to take a derivative of both the equations that I had for solving for A plus and A minus. So these are the equations. I'll write them again. So from equation 1, what we get is, actually I'll not write I think it's not necessary to write all the details, so I'll just write the final thing. So you can just operate this derivative on V of lambda and sigma of lambda, and you'll get two equations. And using those equations, you can see that this expression that you have, you can write it as okay, and then you can use this again once you have this expression, and ultimately the expression you're going to get is this. Now, what you're left to do is just to do some residue calculation, because you have a first order pole at E1 and you have a second order pole at E2. So you have to do a residue calculation, and ultimately you get the expression for R0. This is the expression. You can check this. Okay. So is there a question? Because after this, I'm going to start with these equations. So if you have any questions.
Yes, Siddharth has a question. So can you please go ahead?
Hi. I was just wondering, you didn't make any assumptions on your V of lambda other than that it has support between A minus and A plus, right? Between plus or minus A.
On V of lambda?
Yeah.
I'm just wondering. My V of lambda to be a power series. That's all.
Right. I'm just wondering, in this expression, there's no information about V of lambda other than this A. Right?
Yes, yes.
Whereas in your R01, you had an explicit V prime of lambda, but in this R02, it seems like for any V of lambda, it
and
only
this is
matters.
actually an important point, that you do not have, like, you have the dependence through A only.
I see.
Akhil, you can ask your question.
Our definition of this R of multiple E's for like just a string of R1, E2, and so on, right? And that seemed kind of symmetrical in E1, E2, but these formulas don't.
Which formula?
So R02 E1, E2 is just the 02 level, like genus expansion, but of R of E1, R of E2, R of E, and so on. I mean, R of E1, R of E2 expectation, right? With the distribution. I'm just saying R of E1, E2 is like a 2-point function in E1 and E2, but like it's symmetric. It's that definition seems symmetrical in E1 and E2, right?
Oh,
but,
okay.
But our formulas don't.
I think I made a, I mean, this is E2. I'm sorry. Yeah, thank you for this. This is not lambda. There's no lambda in this equation. We did an integration over lambda. So that was a mistake. Thank you. Another question?
Yeah, you have this. You have these in the like previous formulas also. So like maybe when before you update or something, you need to fix it.
Where?
I mean, none of these formulas are symmetric in E1, E2, right?
But when I have an integral form, I mean, you can see it from here. But
yeah, maybe the first formula in this page, like maybe previous formulas it works out, but I don't know. This the first formula, is it?
But there is an
maybe, yeah,
integration
okay.
over lambda that you have to do. Okay, so
Yeah,
let's-
Pranjal has a question. So
No, I just wanted to ask whether what's the relationship between A plus, A minus, and A? Maybe you already said this. I missed that.
Oh, I'm taking A plus and A minus as plus minus.
Okay, thanks. Thanks.
Okay, let's move on.
Sorry.
Question. Is there another question?
So is only R02 independent of the potential V, or yeah, is there like a,
It depends on V through these endpoints A.
yeah, but like this feature is ubiquitous like for higher pattern, or
Sorry, your voice is not clear.
is this feature ubiquitous? I means for like higher point functions, we'll also we see that this way, means that it depends.
Yes,
through view.
you'll see when we go to loop equations and topological recursion, you'll see. There are a lot of nice properties that appear.
Akhil, you have questions?
Yeah, so I still haven't really followed from the when we started introducing the sigma, but just as a curiosity, like this trick is common for all the ensembles, or this choice of sigma dependent on beta?
Choice of sigma is
So the way we introduce the sigma, I still am not exactly clear on what happened, but would like just the same procedure work for any ensemble? I'm asking.
I have not done this analysis for any other ensemble, but I'm not sure if the same thing works out. So what happens in case of the other ensembles is this factor of 2 here changes to beta. Okay. So this
Right. So I'm asking,
the,
is the square root also coming from that too, kind of thing? Yeah, I guess.
okay, this square root is okay. This square root is actually coming from what cut solution you are taking. So I said I'm taking a one cut solution. That is why I chose it like this. If say you have some like support from A minus to A plus and B minus to B plus, your eigenvalue density is supported in these two disjoint intervals. Then you will choose something like X minus A minus, X minus A plus, and then X minus B minus, X minus B plus. So, okay, I'll tell you one more thing. So this expression of R0, 1 that I wrote here, in case of an n-cut solution, you have to find an appropriate function like I wrote down sigma of x. And as I just told you, how do you choose it? It have to have the same branch, I mean, same branch cut where your resolvent has a branch cut. So you have to choose an appropriate function, say f of x, and then you can write your R0, 1 like this. You just replace sigma with f of x.
Right, but I didn't know why should sigma have a square root branch cut, right? Like, so where did that come
Yes,
from?
we did not know, but as I said, and as Orgo also pointed out, this is just an answer or a trick to find out the resolving.
See, this integral expression where you have introduced sigma, R0 E is equal to some integral with root by root sigma, that is just an identity, right? Like, it just cancels whenever it picks a pole or whatever.
Yes.
I am just asking, like, why not cube root sigma or whatever, something of sigma.
Okay, so one of the place where I used this property that it is a square root function is going from this to this expression, because I said if you take the integral above the real axis or below the real axis, depending on your orientation, your lambda will be, you will have the integral with the plus on one side and you will have the integral with minus on the other side. And since your sigma also changes sign, the overall minus sign does not contribute, it becomes a plus. So then what you are left with is just r0, 1 e plus I epsilon plus r0, 1 e minus I epsilon, and you can just replace it with its average value, which is nothing but half of p prime.
Right. So it's square root because we are taking the discontinuity over it. Right.
Yes.
Okay. Thanks.
Okay, so yeah, let's talk about loop equations. So loop equations are something which define a relation between all these functions r, g, comma, n's, and you can these follow from sort of a translation symmetry of your partition function. So there are different ways to derive these equations. I'll just mention what are the different ways, but I'm going to just show you one way to do it. So let me just start with the partition function again. Now, what I'll say is I'll say that my h goes to h plus some epsilon h to the power k, and I demand that my integral is invariant under this transformation. Or an equivalent way of saying this is you just take this variation, you put this insertion, and you demand that the integral of this derivative vanishes. And so these two ways of looking at it is equivalent, and that you can explicitly check. What I'm going to do is I'm going to write this equation. Okay. So what we have to do is we have to act this derivative once on this and then on this. So when I operate it on h to the power k, I get this term. And when I operate it on the potential, I get this term. Okay, I'll just substitute these two expressions in the equation, and what I ultimately get is this equation. Oh, this is my loop equation. Now, we do not have a single loop equation for a matrix model, but we have an infinite number of them, and you'll find them written in in different number of ways. So the most generic one, which you'll find everywhere, I'll come to that, but this is the loop equation, and I'll do a little manipulation of this equation to write it in terms of the correlators of resolving. So we don't have to do much actually. What I'm going to do is I'm just going to take sum over k from 0 to infinity, and I'll multiply with a factor of x to the power minus k minus 1. I should put it inside. Similarly here, you can check that once you do that, you have the equation in terms of the correlators of resolvent. So yeah, I should not write x here, I should rather write e, so that the notations are consistent. This is the equation you are going to get. Now this is not a connected correlator, so I'll write it in terms of the connected correlators. This is nothing but the connected part. This part.
Excuse me, I have one question. How do you derive these loop equations? Means is there like a first principle way of?
How I just showed the derivation.
Oh, from here. Okay.
So what I'm demanding is that my integral is invariant under this change of variables.
Okay.
And an equivalent way of looking at this is the integral of this total derivative vanishes. This is what I've used. I've just operated this on this and once on this. I've just put these expressions here, and this is the equation that I get. Is that fine?
Yeah, okay. Thank you.
Okay, so in terms of connected correlators, this is your loop equation. You can also call it the master loop equation, and then you can keep on operating with your loop insertion operators to get the higher order loop equations. And,
so actually, I am not understanding the loop concept here. So previously we were drawing those double line notation. So so now we don't have anything like that. Like it is loop in correlator, right?
yes, I'm going to write it in terms of RG comments.
Okay, so in the previous,
I mean, because whenever I write a correlator, you can always use the genus expansion to write it in terms of RG command.
so in previous slide, actually, can you explain this why you are doing this once more?
Why?
Why like to derive loop equations? It is not totally clear where you are considering loop.
Where am I considering?
It's why you are considering these to derive the loop equations.
I think she's asking why are you calling it a loop equation?
Yeah.
Okay, I am calling it a loop equation because it gives me a sort of a recursion relation between all the RG comma n. So for example, if I want to evaluate R1 comma 1, the loop equation tells me that I just need R0 comma 1 and R0 comma 2 to evaluate it.
Okay.
And you can go so on for any higher RG command.
Okay, so higher loops means higher genus.
Yes, you can say that. So this what I wrote here is the you can say the simplest or the master or the first loop equation, and then we'll write down a more generic loop equation which involves the higher order RGMs.
Okay. Okay.
I think if the name loop is confusing, you can just call them like word identities. I mean, they're the same thing.
Yes.
So.
Okay, so I'll just mention what other ways you can derive these equations. So if you do not like this way of doing it, then you can just start with your partition function and then make this change of variable, and you choose your delta h to be 1 over e minus h, and you will get the same equation. And to go to the higher order loop equations, either you can keep on operating with the loop insertion operator, or instead, again, if you'd like to derive it starting from the partition function, you can just put some more insertions here, and you can from the invariance of the partition function under this transformation, you can find out your loop equations. Okay, but yeah, I'm not going to derive all the loop equations. I'll just write the first two of them and then the general one. And if you like, you can check these, or I've already shared a reference on Slack, so you can follow that. Okay, and if you want to write it in terms of eigenvalues, then your equation will be this. Write everything in terms of eigenvalues. Okay, and let me just mention one more way of deriving it. So you had your loop insertion operator, dv of x. If you want to use them, then you can define another operator from these. And just write this equation. So all these are equivalent ways of deriving a loop equation. Okay, let's just focus on our first loop equation for some time. So this was my equation. I'll just, okay, so this is my equation. Write it. I'm just putting the expression of the resolvent. And what we're going to do is we are again going to do a genus expansion. So if you do a genus expansion.
Sorry to disturb you too, but you have like around 10 minutes.
Okay. Thank you. So yeah, so we are again going to do a genus expansion. So if say if you take this, you will get something like 0, 2, 2. And then you can again do some manipulations, and we can write the equations order by order in L. So what I'll also do is I'll multiply this equation with 1 over L square, and then I'll write the equations order by order in L. So the first equation that I get is this. And I'm writing it in a particular form because that will help me later on. So this 0 here just means the leading order. And then the next order will be this. This one is just to denote that it's the next order. So yeah, these things here are something that we do not know. But when we go to the topological recursion, which is nothing but a reformulation of this loop equation, we'll see that even though we do not know these terms, we can still evaluate all our functions. So let me just write a generic loop equation and then I can stop. Okay, so this is my generic loop equation. There are some notations that I need to explain. So I will do that. So this I is nothing but set of these parameters x1 to xn, and these sum here is over all the subsets of I. This mod j denotes the number of elements in J. And this notation, I think you're familiar with. It just means that you are just taking your I and remove all the elements that you considered in J. And this PGN is a polynomial in X, which is nothing but a generalization of this term. This term here, you can write it as P0, 0. Let me write the expression for this. Okay, I actually write the expression for Pn, and then I'll just say that the genus expansion, the coefficients in the genus expansion are my PG comma n, because anyway at the end we are not going to need the need this this function. So I'll just write this. So I've written x here, or so you can also write e in place of x. These are just the variables. And then I'll just say that it makes a genus expansion. Yeah, so if it should be 2 here, but since in this equation, yeah, okay. So you might see it in like in some references, you might find it that this has a factor of L multiplied with it. So then you'll see the genus expansion will be 1 minus 2g minus n. And if you do not have an L here, then the expansion is similar to all the other correlators, which is 2 minus 2g minus n. So the only point is that you can also write a genus expansion for this polynomial, and that is what we are going to use here. And since we are never going to need the explicit form of this polynomial, I am just going to keep it as PG comma n. So I'll stop here and you can ask if you have some questions.
Okay, I have one question which is like slightly unrelated, but like this expression of the loop equation, it seems like kind of what you have in when you're doing computing a amplitude, like string amplitude, when you're integrating over the moduli space of world sheet. It kind of seems like in the degeneration limit where you have where the Riemann surface breaks into like smaller genus endpoint functions, and you have a regular piece which is just like this PGN kind of thing. Is there like a known parallel, since I've heard that matrix model is used to compute certain string amplitudes?
Yes, there is, and I think Pranjal can explain it better. Probably he's going to talk about similar things.
Okay.
Pranjal here.
Yes. So in this part of, I think in the second lecture tomorrow I'll be discussing the relation between the volumes, Weil-Peterson volumes, and the loop equations.
So there's like a direct parallel kind of.
Yes, it is. The one is the integral transform of the other in some sense. So I'll
Oh,
discuss
okay.
that.
I see.
So I'll probably need half an hour or 45 minutes more to finish up everything. So I'll continue tomorrow, and then Pranjal can start.
I have a question. What do these arrows in your propagator mean?
Okay, so these arrows actually these are related to the fundamental and anti-fundamental representations of the unitary group. But yeah, I cannot tell you more about this. I guess I can just say this, or probably Orgo, if you can, is Orgo here? If you can say something about that. So these are related to the fundamental and anti-fundamental representations of the unitary group.
Okay. And what is the meaning of propagator? Like, is there a physical significance like in QFT?
So here, actually, as such, there is no significance because you are just dealing with a mathematical model. This is not some real theory. So we are just drawing a parallel. So here the propagator is not like what we have, like we cannot interpret it like we have in a normal quantum field theory.
Okay.
Basically, there is no dynamics here. It's just the potential. There is no kinetic term.
You can stop the recording. And yeah, let us thank Neetu for the